Hello and welcome. Equilibrium of rigid bodies, exam question. Unfortunately, this one doesn't have a diagram, and this you can barely read the writing. I even left the watermark, my watermark from my book. So I'm gonna have to read the question as I'm going along and do the diagram, which is of course the most important thing. Okay, so this is about a ladder against the wall. I've done already a question on this topic. This is quite a challenging topic for a lot of students. So let's see how we start this type of question. First of all, we need to start with a good diagram. A good size diagram is that which is roughly half the page, an A4 page. So make sure you have left yourself enough space to put the extra bits of information normally required by this question. So this is now my ladder and is resting against the wall. And now I'm going to read the question to you and start annotating the picture. I often use a lot of colors for this type of work because it is actually useful to see the different things. A non-uniform ladder, that means the weight is not acting at the center. Of weight 180 newtons. It doesn't really matter where we mark the weight. It's highly unlikely the weight will be here or the other end. So let's mark it somewhere here. You can even mark it at the middle point, as long as you know it's not necessarily the midpoint of the ladder. And this is 180 newtons, not 180 G, just 180. And the ladder has length 6 meters. I've took this information in, but I'm not marking it. I'm going to put the lengths in at the very end. Rest which is end A against smooth horizontal ground. Okay, that's A, and the ground is smooth, so that means there's no friction acting there. However, there is a normal reaction, and the normal reaction between the ground and the ladder, I normally call it R, and it's NB, so B is now against the wall, against a rough vertical wall. So first of all, we're going to have a normal reaction. I don't like R1, R2. I'm going to use capital N for normal. And there's friction there. So which way is friction going to be acting? Well, the ladder wants to slide down. Friction will try to stop descent from sliding down. So the friction must be acting in this direction. Is the friction limiting? Is the ladder at the point of slipping down the wall? The answer is it doesn't say. It says the coefficient of friction between the ladder and the wall is 1/4. That does not necessarily imply that the equilibrium is limiting. So all I'm going to do is mark my mu is equal to 1/4, coefficient of friction. And for the time being, let's leave it without any marking till we read the question a little bit more. The center of mass of the ladder is 1.5 meters from A. So in fact, this distance is 1.5 meters. The whole thing is 6. So far this is 1.5 and this is 4.5 to be marked at the end. The ladder lies in a vertical plane perpendicular to the wall and the ground and is inclined at an angle theta to the horizontal. So this is the horizontal. So the angle theta is actually given, but is not given exactly as in degrees. It's actually giving us the exact value of its tan, where tan of theta is equal to 2. So that's as good as knowing the angle, the sine, cosine, and everything else. Okay, the question continues. There's a man. A man can prevent the ladder from sliding down the wall by pushing the bottom of the ladder with a horizontal force F. So there is a man at the bottom of the ladder, perhaps on his knees, and he's pushing the ladder towards the wall. So the force is providing is actually something like that, as my pen is pointing, but of course I'm going to mark it inwards, and he said that force is F, and it doesn't tell us what it is, and there's a key word there. A man can just prevent the ladder from sliding down. What does that actually mean? It means the equilibrium is limiting here. It means basically the man is pushing so lightly, the ladder is almost ready to slide. And therefore, this will now be mu n. Mu times the normal reaction. Normally we're using R's, so I hope it's not confusing that I used N up there. If you want, when you do your own diagram, mark this as N and swap the R's there. It doesn't really matter. Okay, I'm ready now does he ask? He's asking us to find the value of f. How hard is this man pushing, basically? So we're trying to find the value of f. So I'm ready now to finish off my last bits in the diagram. The last bits of the diagram are as follows. First of all, decision number one is to say, okay, where I want to take moments, because of course there are three equations in these problems. Balance vertically, balance horizontally, and of course take moments about a suitable point. The points in question are probably A or B because each of them has two forces, and I'm gonna go for A. No, I prefer A. I just like A. Not really. It will work just as good if you go at N, I think. And by pivoting at A, F and R will have no moment. Immediately, as soon as I do that, I'll draw perpendiculars to the ladder at the rest of the points that have forces. So here and at B, at where the center of mass is and where B is. Next, I need to put the lengths so I don't forget. 1.5 here and 4.5, of course not drawn to scale here. And there's one final thing, is to mark the angle theta in this neighborhood and in this neighborhood, because of course I will need to resolve these forces. First of all, I'm going to draw this angle here, theta, because of course that's alternate angles there. They're forming a Z, so that's theta here. And this I need to resolve N, so there or there. And I need, of course, to know if my theta is here. Let me just put another little extension there so we can all see it there. Okay, so for the mu n, as marked in the picture, I need to know is theta on this side or on this side. It's clearly on this side here, because of course, this is now theta, this is 90 minus theta, and therefore is back to theta. What about this one? We can perhaps see a right angle triangle here, and if this is theta, this is 90 minus theta here, and therefore right angle here again, 90 minus theta here, and theta here. Whichever way, geometric way you have for solving your problem, please do. It's important we mark the angles correctly. So first of all, write two simple equations. Forces up equal forces down. What do we have for this? R is acting upwards, plus the mu n acting upwards is equal to the 180 downwards. So that's balancing in the vertical direction. Horizontally, forces to the left equal forces to the right. To the right we got the N here. To the left we have the F, which we're trying to find. F, remember, is let me just write it here. F equals question mark. This is what we're trying to do. Okay, now the moments equation. This is now where the difficulties, and this is the most important equation that we really need to learn how to take moments in a situation like this. We're going to split the force 180, the force N and the force mu N into two components. I'm going to mark them in purple in the picture. So one is acting along the ladder, one perpendicular to the ladder. So the same thing, the N will have a component that goes like that in this side, and a component which goes like that perpendicular to the ladder. The mu N again, it will have a component perpendicular to the ladder. So it's actually going to be something like that. A little bit difficult to draw there. That's what I mean, you need a good diagram. And as you can see, I'm using colored pens for that reason as well, so I can see things. And there's another component along the ladder. Now, when we're taking moments, any force or component of the force which goes through this pivot at A has no moment. This has no moment. F and R, of course, don't have moments. This component, no moment. And of course, those two, because they're acting out through the pivot, no moment. So if we imagine we hammered, put a nail here, and this wall is not there anymore or anything, and we can swing the ladder like a swinging door, left and right. The only things that can swing it is this force can swing it to the left in an anti-clockwise direction, and those two components can swing the ladder in a clockwise direction. So now we need to calculate moments. Okay, we're starting first of all by looking at this force that is, or component rather, of the force which is acting on its own and is trying to swing us in an anti-clockwise direction. 180 which component is that? The angle is on this side, so it's 180 cos theta, times the distance from the pivot, which is 1.5, is equal to, now, because that's the only one that is anti-clockwise, is equal to the moment of those two forces that are working together. So first of all, this component comes from the n. So n, is it the cos or is it the sine? The cos is on the side of the angle, so that's the sine in there. So that's n sine theta, times the distance from the pivot, which of course is 6 meters. Plus, we have another one that's acting together, so that's this one here. This came from the mu n. So this is mu n. I'm going to put the numbers obviously at the very end. The theta is on this side, you can barely see it there in green. So it's on the side of the angle, so that's mu n cos theta, times the distance from the pivot, which of course again it is 6. So we're trying to find f. We're still going to stay with this equation because this has a lot of stuff there, so we're going to tidy this up. 1.5 times 180 is 270 lots of cos theta, is equal to 6n sine theta plus 6 mu n cos theta. Okay, what can we do next? We can put a few bits in. First of all, because we're trying to find f and we have n's here instead, it makes sense to just put f instead, because that's of course what we want to make the subject. And also the mu is a known quantity, is a quarter. So let's put some of these numbers in. So 270 cos theta is equal to 6f, because n and f are the same, sine theta. And mu is a quarter, so quarter of 6 is 3 over 2, 1.5. So plus 3 over 2. The n, I'm going to replace it also with f, and then we go cos theta. How does that look? It looks not so great at the moment, but it's not that bad. We need to use this fact that the tan of theta is equal to 2. Of course, we can do inverse tan of 2, 63.4 and or whatever to 1 dp, then find the sine and the cos of this 63.4, and we'll have here a few ugly decimals, but it will be done. I'll be able to find f. But there's a better way of doing this, and we notice that if we divide this equation through by cos theta, these two causes will vanish, and this sine, when it gets divided by cos, it'll turn into a tan, and once it turns to a tan, I can replace it by a 2. So that's my plan. 270 divided by cos theta, will clear that, is equal to 6f sine theta divided by cos theta is tan theta, plus 3 over 2 f divided by cos theta, all of this is gone. So now my next line, quite obviously, put my tan in, so that's a 2, 12f in there, plus 3 over 2f. You can just put it together, the 12 and the 3.2, and then divide the 270 by that. I don't have a calculator, so what I'm going to do instead, I'm going to double my equation very, very quickly. So 540, you don't have to do that, as I just said, just put your calculator, of course. Double that is 24f plus 3f. It makes it a lot nicer to actually deal with. That's 27 lots of f is equal to 540. And now myself, I can actually see that my f in this particular case is exactly 20. Units are not required. It's in newtons, of course. I avoid putting newtons in mathematical problems, but you please feel welcome to do so. You will not lose marks by not putting units in there. I hope you followed this problem. That's problem number 2 on rigid bodies, and I will see you very, very soon. And this is, of course, the end of this lesson. See you soon.